Hello, my name is Trevor Canham. I'm going to be presenting the work that I did with SaiKiran Tedla, Michael Murdoch, and Michael Brown called Gain-MLP, Improving HDR Gain Map Encoding via a Lightweight MLP. In the past few years, the displays on our phones and our televisions have been improving such that they can show more vivid saturated colors and also brighter and darker colors. And I just have a few images here to illustrate that. The first one is tone mapped into a standard dynamic range display encoding space. And the next image is the same scene, differently tone mapped into a high dynamic range encoding space. So you can see that the high dynamic range encoding space is more dull and lower contrast than the standard dynamic range encoding space, which may be counterintuitive. So this is the impact of the display space encoding. Since the high dynamic range display shows colors that are brighter and more vivid, its encoding space should be much larger than the image it's containing. And the result of that is this sort of low contrast look. But throughout this video, we're going to be transforming these high dynamic range images to sort of an intermediate dynamic range space that most displays are capable of, called P3. And I want to illustrate how these are differently tone mapped. So first, I'm going to show you the standard dynamic range image encoded in the high dynamic range space. I'm going to compare it now to the high dynamic range image in the high dynamic range space. Now going back, so you might notice the snow on the mountain is losing a lot of detail when we go to the standard dynamic range tone mapping. And if we re-represent that in the proper color space, you can see the effect of this is to sort of generate a high contrast appearance of this image on a standard dynamic range display. Okay, now let's take it in the other direction. If we take the high dynamic range tone mapped image and display it in the standard dynamic range space, we get this. We can see now that the image is very dim and is very high contrast, but overall most of the details are dark and we can't see them. And so this illustrates the fact that the standard dynamic range display space cannot represent the high dynamic range tone mapped image. So I just wanted to show here the range of interpretations an image might have. An encoding scheme that's intended to account for this should not limit the artist into using any particular set of image editing operations. One such color encoding scheme has been introduced, gain maps. These maps can account for any type of image editing operation because they are a pixel-wise translation function from the input SDR image and the HDR image. This map is derived by dividing the HDR image by its SDR counterpart, more specifically by its SDR counterpart encoded in the HDR encoding space. As you can see, making this transformation makes a large difference on the image, but what actually comes out of this ratio is not this image, but this image, which obviously can't be represented here on the display. Likewise, it's numerically difficult to encode these maps with standard encoding techniques, so the following equation is applied to normalize these values. So this is a very favorable encoding scheme in the sense that it's not restrictive to artists. However, the drawback is the file sizes. So the various documents and white papers suggest making the encoding more efficient by downsampling and decreasing the compression quality. Unfortunately, these operations are quite limiting and result in a number of artifacts, as we can see in these examples. But in our previous work, we showed that a small modification to the gain map formula allows us higher reconstruction quality at around the same file size. We obtain these exponential residuals by dividing the log of the HDR image over the log of the SDR image. This modification resulted in residuals which were better distributed throughout the intensity range, resulting in a visible reduction in artifacts. In this initial experiment, we demonstrated the limitations of traditional compression. Traditional compression methods rely on the assumption that dense details are less likely to occur in natural images, but the issue with the assumption is that dense details do exist in photographs, and when they show up, the details get lost due to quantization. In recent years, novel encoding schemes have been proposed which avoid quantization altogether. The input to the network are pixel coordinates, or locations in the image. These coordinates are embedded as sign functions and passed into a small neural network, which is optimized on a per-image basis to reconstruct that particular image. So, in this sense, the image is represented by the weights of the neural network. With these continuous sign functions, we can represent image data more efficiently at the cost of the computational stress of optimizing them. Following this trend, we introduce a neural network for predicting Gain-MLP encodings, where instead of just taking in the pixel coordinates, we take advantage of this encoding paradigm where the SDR image is present, and we also pass in the SDR red, green, and blue pixel value at that coordinate. Then we optimize the neural network to predict the Gain-MLP, which we have at the input, and the Gain-MLP can be represented in 10 kilobytes. We combine this with the Gamma-MLP strategy. You can run the MLP in both of these configurations. Finally, in order for these neural networks to optimize in a reasonable time frame for encoding a single image, in our case 3 seconds, it's important to start the neural network with plausible initialization weights. To initialize our network, we generated a series of random color noise patterns and passed them through a generic DaVinci Resolve tone mapping to return HDR-SDR pairs. Using 50 500 by 500 resolution chromatic noise images, we pre-trained our MLP network for 10,000 epochs to get our initial starting weights. In the present work, we conducted a series of experiments using a couple datasets. The first one contains 30 HDR images from the camera manufacturer ARRI. The images were manually tone mapped by Kike Cadenas. In this work, we re-tone mapped this dataset using methods from Reinhardt, which is exposure-based, Drago, which is a logarithmic-based tone mapping, and Larson, which is a histogram equalization-based tone mapping, in order to compare the effect of tone mapping on the encoding schemes. We also use the dataset of Chen, which contains various product demo reel and Hollywood movie images that were uploaded to YouTube and processed via the automatic tone mapping of YouTube. Averaging over all of these images and quantifying our results in terms of the quality of HDR reconstruction after encoding and decoding, we can see that in bold white numbers, the Gamma-MLP's version of our MLP method performs the best and has among the lowest data footprint, beating out other MLP-based methods, as well as significantly outperforming the traditional compression methods. We can see that the Gamma-MLP strategy improves results in the case of MLP encoding, as well as traditional encoding. The worst results for each metric are shown in blue. We also performed a rate distortion analysis on the proposed method and several alternatives. The results show that the proposed MLP shows robust performance at small model sizes. While qualitative results are difficult to demonstrate in encoding applications, here we show that the MLP network avoids errors and artifacts from traditional compression demonstrated with the Gain-HEIC method. Interestingly, in the case of HEIC encoding, we can see that Gamma-MLPs in this case help reduce noise. Comparing against the different MLP-based methods, we can see that the proposed method has the best reconstruction quality. In conclusion, multi-layer perceptron-based neural network encoding schemes can produce high-fidelity, high-efficiency encodings of tone mapping functions that are non-restrictive to the image editing process. However, this comes with the limitation of increased computational burden to optimize on a per-image basis. What do you think? Is this a good idea to use neural networks to encode HDR images? Come to our poster to let us know. Thank you for listening.